Tonight, we're asking one question about the ocean. What if the largest predator that ever lived in it never went extinct? Megalodon has been gone for nearly 4 million years, and everything that grew in its absence is the ocean we've always called normal. This is what happens when you put it back. Most people have a version of Megalodon already loaded in their head, a great white shark, but larger, angrier. The same basic shape, the same blunt nose, the same thick chest, just scaled up until it becomes something from a nightmare. That image has been in every film, every documentary thumbnail, every diagram in every natural history book for decades. It feels settled. It feels like something we know. The problem is that almost every detail in that picture is wrong, and the science that established it was built on a fundamental misidentification that stood unchallenged for over a century. Megalodon was classified in the same genus as the great white in 1835, based largely on tooth similarity. That classification shaped every reconstruction that followed: the body shape, the proportions, the behavioral assumptions. The whole Hollywood version of this animal descends from a single taxonomic decision made nearly 200 years ago, before modern paleobiology existed as a discipline. And for a long time, there wasn't much anyone could do about it. Megalodon left almost no skeleton behind. Sharks are cartilaginous animals. Their bodies don't fossilize the way bone does. What we found were teeth and occasional vertebrae, and very little else. Reconstructing a complete animal from that evidence requires inference, and the inference was shaped by the assumption that the great white was the right template. But the assumptions were wrong, and the evidence that finally corrected them came from a single fossilized column of vertebrae sitting in a museum in Brussels, a specimen that had been waiting, catalogued, and overlooked, while the wrong version of this animal appeared in theaters around the world. But the problem with a misidentification that old is that it doesn't just shape one reconstruction. It shapes everything built on top of it: every film, every museum exhibit, every behavioral assumption, every calculation about how this animal moved, fed, and competed. The 1835 classification didn't just give Megalodon the wrong family. It gave the animal the wrong body, the wrong proportions, the wrong hunting posture, and the wrong place in the evolutionary tree. Every scientist who worked from that foundation was answering a slightly different question than the one they thought they were asking. The compounding effect of that error runs deeper than the physical reconstruction. If the body shape was wrong, then the behavioral models built on that body shape were wrong. The assumptions about how fast it could turn, how it approached prey, how it used depth and angle in an attack, all of it was derived from the proportions of a different animal entirely. Scientists weren't just picturing the wrong shape, they were modeling the wrong hunting mechanics, the wrong energetics, the wrong competitive relationship with every other large predator in the ocean. A misidentified body produces a misidentified animal at every level of analysis. But there is a harder problem underneath this one. Even if the classification were corrected, the animal still leaves almost nothing behind that can definitively settle the basic questions about what it looked like. No complete skeleton has ever been found. The cartilage dissolved, the soft tissue disappeared. What paleontologists have to work from is teeth and occasional vertebral fragments, the hardest, most mineral-dense pieces of an animal that was otherwise built from material the ocean consumed without a trace. Reconstructing an animal of that size from fragments is not the same as knowing what it was. It is inference, constrained by what survived, guided by comparison to animals that are themselves imperfectly understood. The question of what Megalodon actually looked like was always a question the evidence wasn't quite equipped to answer, until one specific specimen changed what was possible. So here is what Megalodon actually was, not the stocky, thick-jawed great white stretched to cinematic proportions. Something genuinely different, and in many ways, more unsettling. The 2025 study, led by paleobiologist Dr. Kenshu Shimada, involving 28 international scientists, changed the picture completely. They worked from a fossilized vertebral column discovered in Belgium, now catalogued at the Royal Belgian Institute of Natural Sciences in Brussels. That column alone measured 11 meters. Just the trunk, the head and tail were missing. So the team cross-referenced proportions from 165 living and extinct shark species to reconstruct the full animal. The head accounted for roughly 16.6% of total body length, the tail 32.6%. That puts a standard adult megalodon at around 16.4 meters, with a 1.8 meter head and a 3.6 meter tail. But a second specimen changed the ceiling entirely. A vertebra found in Denmark, 23 centimeters wide, suggests some individuals grew far beyond that standard estimate. The team's calculations put the upper bound at 24.3 meters, nearly 10 meters larger than previously assumed, roughly the length of a blue whale, weighing close to 94 tons. And the shape was nothing like the old Hollywood version. Megalodon was streamlined, with long pectoral fins for lift and control, a flatter, wider jaw, and a shorter nose, closer in profile to a lemon shark scaled past any plausible limit than to the blunt-headed monster from the films. That shape is actually why the animal could grow so large. A stocky body creates drag, which caps speed, which caps size. Streamlining is what allowed Megalodon to keep getting bigger without sacrificing the ability to hunt. The Otodontidae family had been on a separate evolutionary path from the great white for tens of millions of years, and the 2025 study makes that separation unmistakable. A 24-meter, 94-ton, streamlined predator with a jaw wider than a car and a sensory range measured in kilometers. That is the animal this question is actually about. If this is already shifting how you picture the ocean, leave a comment. We're only at the beginning of what that shift actually means. The animal is now corrected. The Hollywood version is gone, replaced by something 24 meters long, 94 tons, streamlined, and built on an entirely different evolutionary line from anything alive today. But knowing what Megalodon was is only half the question. The more important half is what kind of world made it possible for something that large to dominate without interruption for that long, and what that world reveals about why the dominance was always more fragile than it looked. 20 million years is a number that's easy to say and almost impossible to actually feel. For context, the entire human story, from the first recognizably human primates to this moment, spans roughly 300,000 years. Recorded civilization, the pyramids through the present, is around 5,000. Megalodon's reign was longer than our entire existence, multiplied by a factor of thousands, and it wasn't a reign of struggle or decline. For most of that time, the species was at its peak, widespread, abundant, operating without a meaningful competitor anywhere in the ocean. That kind of sustained dominance doesn't happen by accident. It doesn't happen through aggression alone, or through being large. or even through being well adapted in any ordinary sense. Something in the world itself had to be built to support it. Because no species sustains peak dominance across geological time without the environment holding conditions in its favor consistently for millions of years without interruption. What that world actually looked like, what made it so perfectly suited to a predator of that scale, is one of those things that changes how you see the modern ocean once you understand it. The ocean Megalodon lived in wasn't simply an older version of the one we know. The geography was different, the currents were different, and the conditions that made all of it possible were running on a kind of planetary stability that had no internal mechanism to preserve itself. The rain lasted as long as it did because the world stayed a particular way. When it stopped staying that way, the rain ended. Understanding what that world was is the only way to understand why Megalodon could exist in the first place, and why losing it was always an inevitability waiting for the right trigger. But a world that stable is also a world with no rehearsal for instability. Every species that exists in a consistent environment is, without knowing it, becoming more precisely tuned to that environment over time. The traits that help in a warm, prey-rich, shallow water world it's selected for. The traits that might help in a different world, colder, leaner, with faster prey that migrates to inaccessible zones, get no selection pressure at all. Megalodon wasn't just living in a warm world. Megalodon was being shaped by that world, generation after generation, becoming more perfectly fitted to conditions that felt permanent. That process works in both directions. The more precisely an animal is adapted to a specific set of conditions, the more catastrophic any deviation from those conditions becomes. A generalist, an animal with flexible biology, a wide thermal range, the ability to switch prey when one type disappears, absorbs disruption without critical damage. Megalodon was not a generalist. 20 million years of a stable, warm, prey-rich ocean produced the opposite of a generalist. It produced an animal of extraordinary precision, calibrated to conditions that had no reason to change, and therefore no evolutionary preparation for the moment when they did. The stability that sustained Megalodon was also quietly making Megalodon more dependent on that stability continuing. Every generation that passed without cold, without scarce prey, without the need to follow food into thermally hostile water, was another generation that didn't develop the capacity to do those things. The stability that looked like an advantage was accumulating a debt, and debts of that kind in evolutionary biology come due in exactly one way. The reason Megalodon could exist at that scale comes down to the world it was born into. For 20 million years, the planet was running warm, not slightly warmer than today, but dramatically warmer. The polar ice caps were smaller, or in the early Pliocene, nearly absent. Sea levels were 20 to 30 meters higher than they are now. Florida was almost entirely underwater. What we now think of as continental margins were shallow, sun-drenched, nutrient-rich seas that extended far inland from today's coastlines. The Isthmus of Panama hadn't fully closed yet, which meant warm tropical water could flow freely between the Atlantic and Pacific. That circulation kept ocean temperatures stable across the globe. A planetary system distributing equatorial heat outward so reliably that the concept of a cold ocean barely existed in the latitudes Megalodon preferred. The result was a world of biological abundance, operating at a scale the modern ocean doesn't match. Plankton bloomed constantly in the warm, shallow coastal seas. Schools of fish thrived on that foundation. And on top of all of it, a dynasty of marine mammals had taken hold. The cetaceans, primitive medium-sized baleen whales, perhaps 5 to 10 meters long, slower than their modern descendants, less intelligent, and carrying thick layers of calorie-dense blubber. They lived, bred, and fed in those same warm coastal seas year-round, making no long migrations to cold polar waters that a warm water predator couldn't reach. The planet was producing exactly the conditions Megalodon needed, at scale, without interruption, and none of that system contained a mechanism for self-correction. It was stable precisely because nothing had yet disturbed it. That stability was the entire foundation of Megalodon's reign, which means the reign was always one geological event away from unraveling. That world is now visible, a warm, stable, prey-loaded ocean that held every condition Megalodon needed for longer than the human story by a factor of thousands. But a predator operating in that world still had to solve a problem that the teeth alone could never explain. The ocean is vast, dark in most of it, and full of prey that moves in 3 dimensions. Something had to find the target before the bite could happen, and what Megalodon was using to do that is considerably more unsettling than 40 tons of bite force. A predator the size of a city bus, operating in open water, needs to solve a problem that gets harder as the animal gets larger. The ocean is not a small space. It is a 3-dimensional environment where prey can move in any direction, at any depth, across distances that make visual detection essentially useless for anything beyond close range. A wolf can see a deer. A lion can see a wildebeest. A 24-meter shark cannot see a whale from the distance at which a hunt needs to begin to be efficient. Size creates other problems. A large bobby needs large amounts of food, which means hunting cannot be occasional or opportunistic. It needs to be consistent, reliable, and successful at a rate that keeps the metabolism of a 94-ton animal running. A predator that size missing, hunts, or spending more energy on the chase than it recovers from the kill, loses weight faster than it can replace it. The margin for error is narrow. The hunting system has to work. Megalodon solved this problem in a way that makes the teeth and the bite force almost secondary. The jaw was the closing mechanism, but something else entirely was finding the target, tracking it across open water, and positioning the animal for a strike before the prey had any warning. Whatever that system was, it worked across millions of years of ocean, in shallow coastal water and in open deep water, in daylight and in total darkness, across prey that ranged from fish to dolphins to whales. How a 94-ton animal managed to hunt with the consistency that number requires is a question the jaw alone cannot answer. But vision is the sense humans understand most intuitively, and the ocean defeats it almost immediately. Below a few meters of depth, the water filters light selectively. Reds and yellows disappear first, then oranges, until at depth everything resolves into blues and grays. Turbidity from plankton, sediment, and dissolved organic matter can reduce visibility to meters or even less in coastal water. A predator relying on sight in a coastal, shallow water environment is working with a profoundly limited tool, and one that fails entirely at night, at depth, and in murky conditions. Hearing gets closer. Low-frequency sound travels well through water, far better than through air, and many marine predators use it to detect movement at range. But sound alone gives direction without precision. It tells an animal something is moving, not exactly where the target is in 3 dimensions, not how large it is, not whether it's the right prey or an animal to avoid. For a predator that needs to commit its full mass and momentum to a strike, approximate direction is not enough. The cost of a failed strike, when the animal committing to it weighs as much as a loaded freight container, is not trivial. Smell reaches further, and sharks are well-documented users of chemical gradients in water. But following a scent plume is a slow, directional process, effective for tracking across distance, not for the final precise positioning of a strike against prey capable of detecting disturbance and accelerating away. None of the senses humans reach for first come close to solving the problem of hunting large, mobile prey reliably, at range, in conditions where visibility is poor. Something else had to be doing that work. The question of how Megalodon actually killed comes down to two things: the weapon and the guidance system that aimed it. The weapon was its jaw, 276 serrated teeth arranged in 5 rows, each tooth up to 18 centimeters long, roughly the size of a large adult hand. The edges weren't the irregular, coarse serrations of a great white. They were finer, rounder, built for shearing through dense material rather than simply tearing. Bite force estimates run between 20 and 40 tons of pressure. A great white generates around 2 tons. That difference meant Megalodon's bite was capable of severing the tail fluke of a whale in a single strike, or crushing the skull of a dolphin outright. The hunt ended, for most practical purposes, at the moment of contact. But the guidance system is what makes the whole picture genuinely unsettling. Megalodon didn't rely primarily on sight. The broad, flat snout was lined with thousands of gel-filled pores. The ampullae of Lorenzini, a biological electrical sensor array so sensitive it could detect the faint bioelectric field generated by a living animal's nervous system. A fish buried in sand on the seafloor, completely invisible to the eye, broadcasts its presence through those sensors. A wounded whale a kilometer away is a disturbance in the surrounding water column that the shark can feel as precisely as a sound. Running the length of its body was a second system, the lateral line, a network of fluid-filled canals detecting pressure changes and low-frequency vibrations far beyond the range of sight or smell. Megalodon could feel the steady beat of a whale's tail through open water long before any visual contact was possible. This was not a predator that located prey by charging in the direction of splashing. It tracked pressure signatures from hundreds of meters away, followed scent trails across open ocean stretches, and detected the electrical whisper of muscle contractions through solid water. The 40-ton bite force was the final delivery mechanism for a targeting system of extraordinary precision, and one that operated just as effectively in complete darkness. The weapon is clear now, and so is the guidance system behind it. Megalodon wasn't hunting blind. It was running a sensory system more precise than anything else in the ocean at the time. But there is a question the hunting mechanics don't answer. Megalodon's teeth have been found on nearly every continent. That kind of global distribution looks like unlimited adaptability. It wasn't, and the difference between what it looks like and what it actually was is a question the teeth alone can't settle. Megalodon wasn't a regional animal. It wasn't confined to one ocean or one part of the world, the way most large predators are. Great white sharks are found in specific temperate zones. Tiger sharks stay in tropical coastal waters. Most large oceanic predators have a range that reflects the limits of their biology. Megalodon had no obvious equivalent constraint, at least not one that's immediately visible in the fossil record. The teeth tell that story clearly. They have been pulled from riverbeds, mined from ancient seabeds, and found on beaches across nearly every part of the world. The geographic spread is wide enough that early researchers used it as evidence that Megalodon was genuinely cosmopolitan, an animal that could live almost anywhere the ocean reached. That conclusion was taken at face value for a long time. But a global distribution and unlimited adaptability are not the same thing, and the difference matters enormously when you're trying to understand how the animal eventually disappeared. Something genuinely adaptable, capable of tolerating a wide range of conditions, is hard to kill through environmental change. The distribution was real. What it actually meant about the animal's biology is a different question, and the answer to that question is what the teeth, on their own, cannot tell you. But the biological cost of crossing thermal zones at that body mass is not a matter of discomfort. It is a matter of physics operating against the animal's own size. A mesotherm generates heat internally and loses it through the surface area exposed to surrounding water. Surface area scales with the square of body length, volume, and therefore mass, and therefore metabolic heat production, scales with the cube. At small body sizes, this relationship works in favor of warm-bloodedness. A compact animal retains heat efficiently relative to how much it generates. At the upper end of the size range Megalodon occupied, the relationship inverts in a specific and critical way when water temperature drops sharply. Cold water doesn't just cool the outer layer of the animal. It creates a thermal gradient that the circulatory system has to actively work against to keep the core temperature stable. The larger the animal, the more blood volume is circulating through tissue close to the cold water surface, and the more metabolic energy is consumed simply maintaining the temperature difference between the core and the surrounding ocean. In water that is 10 to 15 degrees colder than the animal's preferred range, the energy expenditure required to maintain that gradient stops being a manageable overhead and becomes the dominant metabolic demand, one that competes directly with the energy needed for movement, digestion, and reproduction. For Megalodon specifically, this meant that following prey into colder water wasn't a matter of tolerance that could be gradually extended. It was a threshold effect. On one side of the temperature boundary, the animal functioned at capacity. On the other side, its own mass worked against it, requiring more energy to maintain temperature than cold water prey could provide, in an environment where the prey had already adapted to thrive. The global distribution of its teeth is not evidence against this constraint. It is evidence of where the ocean happened to stay on the right side of that threshold for long enough to leave a record. Megalodon teeth have been found on every continent except Antarctica. That distribution tells you the animal was genuinely global, not regionally dominant. The streamlined body the Shimada study identified is part of the explanation. A more hydrodynamic shape requires less energy to cover long distances efficiently, the same principle that allows blue whales to traverse entire ocean basins without exhausting themselves. Warmth wasn't optional for Megalodon. Current evidence points to it being a mesotherm, a warm-bodied animal that kept its core temperature meaningfully above the surrounding water, similar to the way modern great whites operate. That partial warm-bloodedness was an advantage in a warm, stable ocean. Muscles always primed, digestion efficient, senses sharp across varying depths and times of day. The animal ran at consistent peak capacity because the environment was consistently holding the thermal baseline it needed. The energy equation is where the constraint becomes hard. A 94-ton body generating internal heat in cold water loses that heat into the surrounding cold faster than any food source can replace it. That is not a matter of tolerance. It is physics. Swimming into polar water at sustained pace was metabolically impossible, not difficult. The Arctic was not an option. The deep trench was not an option. The thermal range Megalodon could actually inhabit was warm, productive, temperate to tropical seas, and the global distribution of its teeth reflects exactly that limit. So the range wasn't a sign of unlimited adaptability. It was a map of where the planet happened to be warm enough. Every continent except the cold one, and that one exception is the entire story. The distribution was a map of where the ocean was warm enough, not evidence of an animal that could survive anywhere. Megalodon's size, its metabolism, the physics of maintaining internal heat at that mass in cold water, all of it created a thermal threshold the animal could not cross. That constraint alone didn't kill it, but it meant that when the world changed, there was nowhere for the animal to go. What actually changed, and why that particular moment was the one the animal couldn't absorb when nothing before it had left a scratch, is the part the fossil record takes a long time to give up. For an animal that dominated the ocean for as long as Megalodon did, the extinction is surprisingly hard to explain. There is no impact crater, no ash layer, no mass die-off of everything around it. The planet didn't convulse. A rock didn't fall from the sky. Whatever happened to Megalodon was not the kind of event that makes a clean mark in the geological record. What makes it stranger is that Megalodon had already survived the kind of change that ends most species. Across its long history, the planet shifted, prey populations fluctuated, ocean conditions changed, and the animal kept going. It had outlasted conditions that ended other large predators without visible strain. The resilience was real and documented. Scientists have proposed temperature drop, prey migration, competition from newer predators, and sea level change as causes, sometimes individually and sometimes in combination. The problem with any single explanation is that Megalodon had absorbed all of those pressures at various points before. None of them, individually, should have been enough. So, the question isn't just what changed. The question is why that particular combination of events, arriving together at that particular moment, was the one the animal couldn't absorb, when everything before it didn't leave a scratch. But the absence of a single catastrophic cause doesn't make the extinction easier to understand. It makes it harder. A meteor impact, a supervolcano, a sudden global anoxic event. These are mechanisms science can point to and trace. The geological layer is there, but timing is precise. The kill mechanism is direct and doesn't require a chain of connected events all arriving in the same window. What happened to Megalodon required multiple systems to fail simultaneously, in sequence, with each failure compounding the next. The prey had to collapse at the same time the nurseries disappeared. At the same time, competition increased. At the same time, the thermal range contracted. Any one of those events in isolation was survivable. Megalodon had absorbed single variable stress before. The animal's resilience across its long history is not in question. But resilience is not unlimited, and it is not equally distributed across all combinations of pressure. A predator can tolerate prey scarcity if reproduction is secure. It can tolerate nursery loss if prey is abundant enough to sustain adults while the population finds new birthing grounds. It can tolerate competition if energy intake is high enough to maintain the size advantage that makes competition irrelevant. The moment those pressures stop arriving one at a time and begin arriving together, Each one closes off the adaptive response to the others. The animal that survived any single one of these pressures couldn't survive all of them landing simultaneously. And nothing in its long history had prepared it for that combination. Arriving from a single geological trigger, it had no way to anticipate. The answer is not a single cause. There was no asteroid, no disease, no catastrophic event. It was a cascade, and it started with a small piece of geography. Around 3 million years ago, the Isthmus of Panama finished closing. The land bridge between North and South America sealed shut, blocking the warm equatorial current that had been flowing between the Atlantic and Pacific for millions of years. That current, diverted northward, became the Proto-Gulf Stream, and that intensified stream carried enormous quantities of warm, moist air over cold northern continents, dumping it as snow, season after season, building the great Pleistocene ice sheets. The planet's thermostat had been rewired, and it was now running cold. Sea levels fell by up to 120 meters as water locked into ice. The shallow coastal nurseries where Megalodon gave birth, the same warm, protected flats that had made reproduction safe for generation after generation, dried out and became land. Simultaneously, the Pliocene saw catastrophic marine megafaunal extinctions. 55% of large marine mammals, 43% of sea turtles, 36% of all large marine species gone. The prey base that had sustained Megalodon for its entire existence collapsed. The whales that survived adapted, grew larger, developed thicker blubber, and began migrating to cold polar feeding grounds where nutrient upwelling produced enormous krill blooms. That is where the food went. Megalodon could not follow it there. The great white shark, smaller and more energy efficient and capable of tolerating cooler temperate waters, moved into the remaining prey. Orcas, with pack intelligence and coordinated hunting, took the rest. The trap was the specialization itself, a body and metabolism tuned so precisely for warm, abundant conditions had no slack to absorb a world that was becoming cold and sparse. One closing isthmus, one rerouted current, and the most successful large predator in ocean history was starved out of existence by a planet that had simply moved on. The cascade is now complete. One closing seaway, one rerouted current, nurseries gone, prey gone, competition closing in from two directions. And the most successful large predator in ocean history starved out of a world that had been built for it. But there is a persistent question that the extinction record alone doesn't fully silence. The ocean is vast and poorly mapped. Science has been wrong before about animals it declared gone. Whether the physical evidence actually rules out a surviving population, or whether the confidence in that ruling is stronger than the evidence behind it, is a question worth sitting with before dismissing. The idea that Megalodon might not be extinct has never fully gone away. It surfaces every few years, a sighting report, a documentary, a photograph circulating online, and each time it gets taken seriously by at least some portion of the public. That persistence isn't entirely irrational. The ocean is large, poorly mapped below the surface, and has a history of producing animals that science had confidently declared gone. The most well-known precedent is the coelacanth, a fish rediscovered alive in 1938 after scientists believed it had been extinct for tens of millions of years. That discovery alone established that the ocean can hide things science has stopped looking for. The survival case for Megalodon draws on that precedent. The ocean's unexplored depths give the argument room to breathe. Megalodon didn't need to be everywhere to survive, just somewhere science hadn't yet reached. That logic has been developed in books, documentaries, and online communities with varying degrees of seriousness. But the physical evidence that would settle the question doesn't require exploring the deep ocean. It requires looking at what any living population of Megalodon would unavoidably leave behind, and asking whether any of that evidence exists. But the problem with requiring physical evidence from the deep ocean is that physical evidence doesn't preserve uniformly at depth. Organic material in sediment-rich, microbially active deep water environments degrades at rates that are short relative to the intervals between sampling events. The argument from tooth absence assumes that a tooth shed in deep water would survive long enough, in recoverable form, to be found by equipment that reaches those depths episodically and samples tiny fractions of the available area. That assumption is not obviously correct. Absence from a record that is itself incomplete is a different category of evidence than absence from a record that is comprehensive. The coelacanth's rediscovery sits behind this problem with specific weight. When scientists declared coelacanths extinct, the evidence was consistent and the logic was the same used to declare Megalodon gone. Absence from the record past a certain date, no physical evidence of continued survival. That logic was wrong by 70 million years for an animal living within reach of a fishing boat. The survival argument doesn't need Megalodon to be common or widespread. It needs only a small remnant population, reproductively functional, behaviorally adapted to avoid the surface, living in a part of the ocean where sampling coverage is thin and preservation conditions work against the evidence that would reveal it. That is a specific, bounded claim. The question is whether the physical record, given its actual limitations, can genuinely rule it out, or whether the confidence in that ruling is stronger than the evidence behind it. No, every claim falls apart under scrutiny. The 2013 Discovery Channel documentary that reignited the survival theory used faked photographs, staged footage, and actors hired to play scientists. It carried a disclaimer most viewers missed and simply ignored. The 1918 accounts from Australian fishermen describing a shark 31 to 95 meters long are almost certainly folklore. The upper estimate would make it longer than any animal known to have ever existed. The 2022 NBC Boston Megalodon sighting off New England was identified as a basking shark. The HMS Challenger teeth recovered near the Mariana Trench in 1873, which appeared unnervingly white and fresh, turned out to be normal fossilized teeth preserved by a thick mineral crust of manganese dioxide that dramatically slowed decomposition. Not recent, not evidence of survival. The biological case against survival is more definitive than any debunked sighting. Megalodon shed approximately 40,000 teeth in a single lifetime across a global range for millions of years, which is why the ocean floor is still littered with fossilized Megalodon teeth today. If the animal were alive anywhere on Earth, it would still be shedding teeth. Fresh, organically intact, unfossilized teeth would be turning up in deep-sea trawl nets, embedded in the carcasses of modern whales, and recovered from ocean floors sampled by scientific equipment. We find none. Every Megalodon tooth ever recovered is mineralized with organic material long gone, dating back millions of years without exception. Modern whale carcasses tell the same story. Tens of thousands have been studied in detail. Whale bones from the Pliocene carry Megalodon's unmistakable serrated bite marks. The silence is the evidence, and that silence spread across 3.6 million years of accumulated physical record, is the straightforward geological conclusion. The animal is gone. The sightings are gone. The faked documentaries, the misidentified basking sharks, the HMS Challenger teeth, all of it collapses under scrutiny, and the tooth-shedding argument closes it further. But there is one version of the survival claim that doesn't rest on a sighting or a photograph. It rests on the Mariana Trench, the least explored environment on Earth, and the straightforward observation that a search you've never properly conducted cannot produce a definitive absence. That argument deserves a precise answer, and the trench fails to provide one on every physical level it can actually be tested on. The Mariana Trench version of the survival argument is different in character from eyewitness accounts and blurry photographs. It doesn't rest on a claimed sighting or a faked documentary. It rests on a fact. The Mariana Trench is nearly 11 kilometers deep, almost entirely unexplored, and represents an environment so hostile and inaccessible that our knowledge of what lives there is genuinely minimal. More humans have stood on the surface of the moon than have visited the Challenger Deep. The few robotic probes that have reached the bottom illuminated tiny patches of a landscape spanning thousands of square kilometers. That ignorance is real, and the argument built on it has a certain structural credibility. A creature that spent millions of years dominating the most expansive environment on the planet might have found refuge in the one part of that environment we've essentially never seen. Not on the surface, where boats travel and whales swim and sonar reaches, but in the deep, cold, pressure-crushed dark we've barely touched. It is the most defensible version of the survival claim. It doesn't depend on a single witness or a single photograph. It depends on the straightforward fact that the deep ocean is a vast unknown, and absence of evidence from a place you've never properly searched is not the same as evidence of absence. The argument deserves a real answer, not a dismissal, but a precise examination of what the trench actually contains and what it would take to sustain something of that size inside it. But if Megalodon did survive by adapting to deep, cold water, that adaptation would not be invisible. Cold water adaptation in large marine animals requires specific, measurable biological changes. A metabolic slowdown, shifts in lipid composition for insulation, cardiovascular restructuring to manage oxygen at pressure, modifications to sensory systems tuned for low-light or no-light environments. These changes don't happen in one generation or 10. They accumulate over thousands of generations, leaving physiological signatures that differ from the warm water ancestor in ways that would be detectable in any recovered specimen. A deep water population isolated for 3 million years would not look like the Megalodon of the fossil record. It would be something different, slower, cold adapted, with different prey, different behavior, and different physical characteristics. And a population of that size, in an ocean where whale falls reach the deep sea floor regularly and provide episodic massive energy inputs, would leave biological evidence. Interaction signatures in the sediment record, chemical traces in the water column from metabolic byproducts, pressure signatures from an animal large enough to displace water measurably, even at depth. Deep water ecosystems are not sealed. They receive material from the surface constantly and export chemical signals upward. The more specific the trench argument becomes, the more precisely it describes what a surviving population would actually require to exist. The more precisely it describes the evidence that population would unavoidably produce, and that evidence, across 3 million years of ocean sampling, has not appeared in any form. Of all the survival arguments, the Mariana Trench 1 deserves to be taken seriously for a moment before it's examined. It isn't an eyewitness account or a faked documentary. It's a structural argument. The ocean is mostly unexplored. The trench is the least explored part of it, and a creature that spent 20 million years dominating that ocean might reasonably have found a way to persist in its deepest, most inaccessible corner. That argument has a logic to it. The problem is that the logic collapses on every level it's actually tested on. Start with food. The deepest dwelling fish on Earth are snailfish, found no shallower than 8,000 meters, partly because there is so little to eat above that depth in the trench environment. These fish are 20 centimeters long, and they exist at the very edge of what the deep trench can support. A 94-ton predator running a partially warm-blooded metabolism would require a food chain capable of sustaining tens of thousands of kilograms of prey per year within a confined, nutrient-poor system. Nothing in that ecosystem approaches that capacity by several orders of magnitude. Then, the temperature. Near the bottom of the Mariana Trench, water sits between 1 and 4 degrees Celsius. For a mesotherm of Megalodon's mass, maintaining internal body temperature in that environment would require burning calories faster than any available food source could replace them. Survival at the metabolic level is not possible. Reproduction, which requires even more caloric surplus, is even further from possible. The ecological argument closes it entirely. When apex predators disappear, the animals directly below them on the food chain expand into that vacuum immediately and measurably. That is precisely what the fossil record shows. Whale body sizes began increasing sharply from around the time Megalodon's teeth stop appearing, and orcas and great whites consolidated the apex role. Neither of those shifts happens if Megalodon is alive somewhere. The trench argument asks us to believe a 94-ton apex predator is hiding in a system too cold and too empty to feed a 20-centimeter fish. That is not a mystery. It is a physical impossibility. The trench is closed. The food isn't there. The temperature is wrong. The metabolic math doesn't work. And a population large enough to be viable would have left chemical and sediment signatures that 3 million years of ocean sampling have not found. Megalodon is gone. The question the title of this video actually asks can now begin, not what Megalodon was, or whether it survived, but what the ocean looks like if it never left. The answer doesn't start where most people expect it to. Everything up to this point has been about an animal that no longer exists. The fossil record, the extinction mechanism, the survival claims, all of it is backward-looking. But the question this video actually asks is a forward one, not what Megalodon was, or why it's gone, or whether it might still be hiding. The question is what the world looks like if it never disappeared. That question is harder than it sounds. The ocean that exists today was shaped by nearly 4 million years of Megalodon's absence. The prey populations, the whale species, the fish stocks, the distribution of marine life at every level of the food chain, all of it developed in a world where a 94-ton predator was not a factor. The ecosystem we have now is the one that developed in the absence of that pressure. Asking what happens if Megalodon is still present isn't just asking about one dangerous animal. It's asking about a completely different ocean, with different prey distributions, different population sizes throughout, and different pressures on every species that currently exists without that predatory weight on it. The consequences don't start with dramatic open water encounters. They start with the fishing industry, and the specific question of whether the commercial fish stocks humans depend on could exist at all in an ocean where they never had nearly 4 million years to recover. But the ocean doesn't reset. Removing a species from an ecosystem and then returning it isn't like removing a piece from a machine and replacing it. The machine isn't waiting with that space preserved. The ecosystem that grew in Megalodon's absence reorganized entirely around the space it left. Every prey population that expanded into that space, every predator that inherited the ecological role, every species that adjusted its range or behavior in response to the new pressure landscape, all of it locked in over that span of time in continuous change. The ocean Megalodon disappeared from, and the ocean that exists now are not the same ocean, with one variable different. This means the consequences of Megalodon's continued presence aren't calculable by simply adding its consumption back into the current system. The current system wouldn't exist. The fish stocks that commercial fishing depends on developed under specific pressure conditions, the absence of a predator consuming large quantities of exactly the prey those stocks feed on. The whale populations that regulate nutrient cycling in the upper ocean developed at sizes and in numbers shaped by the absence of a predator capable of killing them. The coastal ecosystems that nursed those populations to viable breeding density developed in water that was not simultaneously being used as a birthing ground for a predator of that scale. The same removal runs through all of it. The question isn't what Megalodon would do to the current ocean. It is what the current ocean would look like if the removal that produced it had never happened, and whether anything resembling the world we've built on top of it could exist at all. Some orcapods today follow fishing vessels and strip catch directly from long lines, a learned, strategic behavior that costs fishing operations millions of dollars a year. Megalodon, with a sensory system capable of detecting prey bioelectric signatures from kilometers away, would not miss a boat hauling fish. The acoustic and electromagnetic profile of a working vessel dragging a catch through warm coastal water is detectable by any shark with a functioning lateral line. Megalodon would find fishing boats the same way it found slow whales, not by accident, but by targeted tracking. Commercial fishing in warm water zones, which is where most of the world's high-volume fishing happens, would face consistent, large-scale predatory interference with no meaningful countermeasure. A single Megalodon consumed roughly 1,100 kilograms of food per day. A global breeding population sustaining the species across its historical range. Feeding at that rate would exert sustained downward pressure on large marine prey at a scale that would prevent prey populations from rebuilding between feeding seasons. The large pelagic fish stocks that commercial fisheries depend on today developed in an ocean where that pressure had been absent for 3.6 million years. That absence is a precondition of those stocks existing at their current volume, not background context, but a direct cause. And ocean temperatures are now rising. The warm tropical belt is expanding. In a world where Megalodon never went extinct, current climate conditions would be actively supporting population growth, more warm water habitat, more productive coastal zones, more accessible prey range. The species would not be struggling. It would be in a period of population expansion, moving into coastal zones it had been climatically excluded from for the last 3 million years. At precisely the moment human coastal infrastructure is most concentrated there. The ecological impact runs deeper than fishing interference and prey depletion. A global Megalodon population consuming at that rate in an ocean that never had nearly 4 million years to recover from that pressure, would not produce the fish stocks, the whale populations, or the marine productivity that the modern world is built on. But the consequences don't stop at the open ocean, and the geography of where the real threat sits is not where the imagination naturally places it. Where Megalodon actually spent its time changes everything about what a world with it present would look like for the people living closest to the water. The image most people carry of Megalodon as a threat is an open ocean one, something vast moving through deep water, far from shore, in the kind of environment that ordinary life never touches. That framing makes the danger feel abstract, a problem for research vessels and deep-water surveys, distant from beaches and shipping routes and harbor infrastructure. But was Megalodon primarily a deep-water animal? The fossil record is consistent on this point, but the answer may not match the assumption. Understanding where this animal actually lived and why it preferred certain environments over others changes the geography of what a world with Megalodon present would actually look like. If the answer puts Megalodon in a different kind of habitat than the deep open ocean, closer to the continental margins, closer to the concentrations of prey, closer to the zones where human coastal life is most dense, then the question stops being hypothetical. It becomes a question about every major port, every commercial shipping lane, every beach on a warm coastline anywhere on the planet. Where Megalodon actually spent its time is what determines how close the threat would actually be. But the coastline is not a static thing. The shallow, nearshore environment that Megalodon preferred is also the most ecologically productive zone in the ocean, where river nutrients mix with tidal action to produce the plankton blooms that feed everything above them in the food chain, where juvenile fish concentrate before moving to open water, where marine mammals give birth and the biological density is highest relative to the volume of water. A predator of that scale operating in that zone isn't a threat to one species. It is a pressure on the entire coastal food web, affecting prey distribution, juvenile survival rates, and the behavior of every animal that uses shallow coastal water for any part of its life cycle. Prey species that can't retreat to deeper, colder water have no refuge. Species that must use the nearshore environment to reproduce have nowhere else to go. The predatory pressure doesn't distribute evenly across the ocean. It concentrates in the zone that everything else depends on most. What that means for coastal systems built on top of marine productivity is a question that runs deeper than physical danger. The entire biological foundation that nearshore fisheries draw from, the juvenile fish populations, the breeding marine mammals, the plankton-fed food chains, was established in coastlines where that concentrated predatory pressure had been absent for millions of years. Whether that foundation could have developed at all under consistent, targeted predation in the one environment it cannot avoid is a different question than what Megalodon would do to the ocean we have now. Megalodon gave birth in shallow nearshore water, not the open deep ocean, the same nearshore environments that today hold beaches, shipping lanes, fishing ports, and harbor infrastructure. A newborn Megalodon was already 3.6 to 3.9 meters long. The shallow coastal flats were chosen as nurseries because the water depth physically excluded adult competitors. A 16-meter body can't navigate easily through 10 or 15 meters of water. Those nursery zones would span every warm water coastline on the planet, the Atlantic seaboard of the Americas, the Mediterranean margins, the Indo-Pacific shorelines, the coast of Australia. Every major port city on Earth sits inside Megalodon's preferred birthing habitat. Maritime shipping moves roughly 90% of global trade through exactly those warm coastal lanes. Cruise routes, container ship corridors, fishing grounds, all of it runs through Megalodon's preferred habitat. And an animal capable of generating 40 tons of bite force and detecting the bioelectric signature of machinery through water would not treat those vessels as background noise. The scale of impact on maritime activity would be structural, not incidental. The evolutionary pressure that produced the blue whale, the fin whale, and the humpback only existed because Megalodon was gone. With Megalodon still present, the cetaceans that survived would be the faster ones, the deeper diving ones, the ones that minimized time in warm, shallow water. Smaller animals, more evasive animals, built for escape rather than bulk. Smaller, more cautious whales occupied coastlines, disrupted shipping, and a fishing industry operating against a predator it has no way to exclude. That is what the coastline looks like. The coastline picture is complete. Occupied nursery zones, disrupted shipping, smaller, more evasive whales, a fishing industry operating against a predator it cannot exclude from the environments it depends on. Every consequence traced so far, ecological, industrial, coastal, evolutionary, follows from one extinction that happened nearly 4 million years ago. What remains is the question those consequences haven't quite answered. Not what changed when Megalodon disappeared, but what the fact of its disappearance still means right now. In the ocean we use, the baselines we measure, and the version of the natural world we have always taken as given. Every extinction leaves a question that the individual facts don't quite answer. Not what the animal was, or how it died, or what replaced it, but what the loss actually meant. What a world without it became in ways that are still visible, still running, still shaping the things that exist now. Megalodon has been gone long enough that the ocean we live alongside feels like the natural order, the blue whales, the great whites, the fishing grounds, the navigable coastlines. None of it announces itself as a consequence of something that vanished before our species existed. It simply looks like the world. But the modern ocean isn't the natural order. It is a specific outcome. One version of what the ocean became after a particular predator was removed from it. The ocean that exists now is a specific outcome of that one removal, and the consequences of it are still running. The question underneath everything else is simple. What does it actually mean that the ocean we know only exists because this animal doesn't? But 3 million years is long enough to erase the comparison point entirely. There is no parallel ocean, no version of Earth where Megalodon survived, to measure the current one against. The ecosystems we call natural, the baselines marine biologists use to assess ocean health, the population sizes considered normal for whales and large fish, and coastal marine mammals. All of it was established in a world where this particular predatory pressure had already been absent for longer than our species has existed. The baseline is not neutral, it is already the outcome. This matters in ways that are easy to miss. When conservation science identifies a whale population as recovering, the target population size it's recovering toward was set in an ocean without Megalodon. When fisheries management calculates sustainable yield, the fish stock models it draws on developed in an ocean without Megalodon. Every number, every definition of what a healthy ocean looks like was calibrated to an absence that nobody designed and nobody chose. It simply accumulated over geological time until it became the only reference point available. The extinction isn't a historical event that ended when Megalodon died. It is a condition that the entire modern ocean is still living inside, and has been living inside for so long that the condition itself became invisible. What the ocean is now, what it produces, what it supports, and what humans have built on top of it are all shaped by one removal that nobody alive witnessed and no record directly captures. The question of what that removal actually means is not a question about the past. It is a question about the present, framed by the only ocean anyone has ever known. The story of Megalodon is not really a story about a monster. It is a story about a system. For 20 million years, one species sat at the top of the most productive ocean the planet has ever produced. That dominance wasn't a matter of aggression or size alone. It was a precise fit between an animal and a world. Warm, stable, shallow seas filled with slow, blubber-rich prey, and thermal consistency that allowed a partially warm-blooded predator of colossal mass to operate without metabolic compromise. That fit was so exact, so thoroughly maintained across geological time, that the species never needed to change. It was a solved problem, running on repeat for longer than the entire history of human-related primates. Then one corridor of water sealed shut. One geological event triggered a cascade that took millions of years to complete, but the outcome was never in doubt once the first domino fell. The prey disappeared, the nurseries dried up, the thermal zones contracted. Smaller, more adaptable competitors filled every gap the giant left behind as it weakened. The animal that had ruled the ocean for longer than most dynasties in the fossil record could name starved quietly out of existence, leaving nothing behind but teeth. Those teeth matter more than they might seem to. Megalodon shed roughly 40,000 in a single lifetime, across a global range, across a span of time that dwarfs every human civilization combined. They are in the phosphate mines of Florida, in the riverbeds of South Carolina, on the beaches of Australia, in the cliffs of Europe, cold, mineralized, and sharp enough, after 3 million years, to still cut skin. Every one of them is a record of something that existed, dominated completely, and then ended, not with a cataclysm, but with the slow, indifferent rewriting of planetary conditions. The blue whale exists because Megalodon doesn't. Modern shark populations exist because Megalodon doesn't. The fishing industry, the whale migration routes, the coastlines humans have built their civilizations along, all of it is downstream of an extinction that happened 3.6 million years ago and has been quietly shaping the ocean in every direction ever since. The what-if question answers itself. A world with Megalodon is a world where none of that ever had the conditions it needed to develop. The king is gone. The teeth remain, and the ocean that filled the space it left is the only ocean anyone alive has ever known. If this shifted something in how you think about the ocean, or about what we mean when we call something natural, subscribing is the best way to find the next one. Sleep well.